Hello, wonderful people! Here we are in Chapter 13, Universal Gravitation, and today's topic is black holes, which are just a super cool topic. So, we are going to get into some of the nitty gritty about this because who doesn't want to understand what black holes really are? I mean, really. So, what are we looking at? Page 1. When a massive, this is what you need to know coming out of this. When a massive star collapses into a black hole, there is no change in the gravitational field at any point beyond the original radius of the star. So, a black hole is when a star collapses. There's no extra matter being thrown in there, it's just a star, and then it starts to shrink into a tiny dot. So, we're going to discuss this at length. Here we go. There is a candy apple. My grandma Gruber was famous in the neighborhood for making candy apples. Her kids were little kids starting, see, Uncle Tuppy was born in 1942. So he was out trick or treating by 1945 or 6 or so, right after the war. And, uh, and then she had 4 boys and a girl, 5 kids. And, everybody would always come to Grandma Gruber's house at Halloween because she would give out these candied apples, and hers were red like this. Um, you don't see those given out anymore because people don't like handing out uh, raw fruit. It could go bad, whatever. But back in the 40s and 50s and even the 60s and 70s, when I was a kid in the 70s, Grandma was still handing out these apples. But by the time it was 1980, that tradition had stopped. So if you haven't seen any of these, maybe I'm not surprised. You can still buy them in stores and stuff. They are delicious because the red outside is super hard, but it's also kind of plastic and super sticky. Dentists hate it because when you bite it, it will pull out fillings every once in a while. It is that sticky. But kids just love sweet, sticky stuff, so they taste great. So why am I bringing this up? Because this candy apple is made by melting sugar and some other things, and you dip it in there, or you pour it over, and the red liquid is liquid, and then it hardens into the shell after a while. And that's you set them on the tray, and you can see you get a little liquid running off down there, and that was always my favorite part because you got a big extra bite of the candy apple, of the candy itself. And so this is how you see them in the stores. Sometimes people will roll them in coconut or something. I always liked mine plain. So why are we telling this story? Because we are going to coat the whole earth in candy apple. So here's my red candy apple, and I'm going to drip it over the whole earth. And there we go. Now I'm doing a cutaway picture, so you just see the outer crust there, but the whole earth is covered in it. And it hardens. So now this is hardened and it's completely solid, harder than steel. And so there's a buddy of mine, his name's Randall. He's always on his cell phone. And he's walking around the surface of the candy coated earth. And I am going to cast a spell. I'm going to cast a spell and shrink the earth. Now, the earth is stuck to the candy apple, so there's a little bit of a pop as the earth unsticks itself from the candy apple shell. But once it's unstuck, it got smaller and it can keep getting smaller, smaller, smaller. It's going to shrink a bunch more, and I'm going to shrink it a whole bunch more. And I'm actually going to shrink it even more, but I'm not going to make it so small that we can't see it. So I'm going to leave it that size for now. But it is a tiny, tiny little dot. And there's my buddy Randall still walking around on the candy apple shell. Okay, do you like the story so far? Great. So now, here is our force of gravity equation. You recognize that? And here's Randall. and we're going to calculate the acceleration that Randall's undergoing. It's force divided by mass, and there's the mass of Randall. And the acceleration, as we all know, is 9.8 meters per second squared at the surface of the Earth. So I know the acceleration Randall's got here on the surface of the Earth, and I'm going to take this equation, and I'm going to take the F, I'm going to divide it by M to get the A. So now this A, 9.8, equals this. But that means I have to divide this side by an M. So I put the little m, the mass of Randall, on the bottom of the fraction over here. Now we need some more room to see all this. So I'm going to move the Earth over there. Micro mini Earth is still in the center. Randall's walking the surface. So there's the gravity equation, g(mm) divided by distance squared. I divide by the little mass of Randall to get the acceleration. Oh, I forgot to cross it out. And then, so A equals gmm divided by d squared m. And then you can cross out the little m on the bottom and the little m on the top. And you get this. Now, this gm divided by d squared gives us the 9.8 meters per second squared. This tells us the acceleration at the surface of the Earth. Now, the distance is from the center of the Earth, way down there, to the distance where Randall's standing, okay? So that distance is 6,378 kilometers, or kilometer. I don't care what you say. Now, the mass of the Earth is good old 5.98 times 10. Oops, that's supposed to be to the 24, 10 raised to the 24. And g is a constant. That's always the same number, 6.67 times 10 to the minus 11th. And there are the units. So I've got GMD here, and there's GMD to calculate 9.8, the acceleration that we have at the surface of the Earth. Okay? So there's GMD squared, there's my GM and D. Now what I'm going to do next is, so there's the same GMD here is the same GMD here, diameter 6,000 kilometers. Instead of worrying about 9.8, I'm just going to call it 10 meters per second squared. But now, instead of having GMD be this, I'm going to change the D, and I'm going to cut it in half, and I'm going to round it off a little. So D is 3,200 kilometers. Now, remember, I was calculating acceleration. Acceleration equals GM divided by D squared. So if I move Randall halfway down to the Earth here, his new acceleration is going to be 40 meters per second squared. So there's, not Randall, that's a buddy of his. What's that guy's name? I can't remember his name. We'll call him Chad. So Chad cut a hole in the candy apple, stuck a rope in it, and is halfway down to the Earth. So he cut the distance in half to get 3,200, and now he feels an acceleration of 40 meters per second squared. Remember, all the mass of the Earth is still right here. This isn't like yesterday where he's digging a tunnel and you're leaving some of the mass above you. No, all the mass is down there at the point at the center. Oops, I jumped ahead. So his acceleration here is now 40 meters per second. And now he's going to cut that distance in half again. So instead of 3,200 kilometers, he's 1,600. He's 3/4 of the way from the surface down to the tiny mini micro Earth that's in the center. And once he's 3/4 of the way, now his acceleration is 160 meters per second squared. So that's 160 meters per second squared. If you jumped off a building, after 1 second, you would be going 160 meters per second, which is over a couple hundred miles per hour. I should have done the math, but I can't off the top of my head. That's really, really fast. Okay, that's a lot of acceleration. You would weigh over a ton. If you put your book bag on your back under this acceleration, that book bag would weigh over a ton. So now he's going to drop even closer. But I made the Earth bigger so we can see to keep everything to scale. So now he's even closer. I just made this bigger, magnify, that's the word. And now he's at a distance 800 kilometers above mini micro Earth. And now his acceleration is up to 640 meters per second squared. And he's going to drop down further again. Halfway from there, oops, I hit the wrong button. From 800, keep hitting the wrong button. From 800 here, halfway, there's 400 kilometers above mini micro Earth. And now his acceleration is at 2,500 meters per second squared. And we're going to keep getting closer. So now you can see the Earth got even bigger. I magnified this even more. And here he is. Now he's 200 kilometers above the Earth. Now his acceleration is over 10,000 meters per second squared. I mean, at that speed, if you were on the moon and the Earth was pulling you at this acceleration, you would go from the moon to the Earth in about 10 seconds. Actually, under 10 seconds. From the moon to the Earth in under 10 seconds, just from the gravity. If the whole trip was at this, 10,240 meters per second squared. That's a lot of acceleration. But you know what? We're going to send Chad even closer. So there he is 200 kilometers away. Now he's 100 kilometers away. And now his acceleration is 40,000, call it 41,000 meters per second squared. Now, this is 100 kilometers away. That's a lot of distance. But now I want to zoom in from 100 kilometers down to 2 kilometers. So I'm going to have to magnify this picture again. Okay, you ready? Well, the Earth is bigger. And mini micro Earth is still in the center. It's still mini and micro, very tiny. And I want to put a green arrow to mark this height. So here at the distance of 2 kilometers, right there, the acceleration is 102,400,000 meters per second squared. Okay? That is just a crazy big number. Now that's at a height of 2 kilometers. Next, I'm going to go to a height of 1 kilometer. So you see he was here, now he's going to drop down halfway, and I'm going to put a purple arrow in there to mark that height. And at this height, when you do the math for 1 kilometer, now the acceleration is 409,600,000 meters per second squared. Okay? So, just to review real quick, we started at the surface of the Earth, and then we dropped to get in closer and closer. And remember, all I'm doing is taking this d and plugging it into this equation to get the acceleration that the person feels. So g is a constant. The mass of the Earth never changes. It's all down there in that tiny little micro mini Earth in the middle. So my d is getting smaller. So as my d gets smaller, my acceleration gets bigger. So here he is, what's that, 3/4 of the way down, and 800, 400 kilometers, 200 kilometers, 100 kilometers. And when he gets down to 2 kilometers and 1 kilometer, that's where I'm making these notes, 100 million and 400 million meters per second. Okay? So then we move on to, let's zoom in on those two heights and talk about this. Okay? We're just going to zoom in on this. So there we zoomed in. I've also put Chad's twin brother. So we're looking at these two things, these two situations. A distance of 2 kilometers up there, 1 kilometer here, and there's mini micro Earth with all the Earth's matter still in that tiny little dot. All right, here we go. So here is the number that is the speed of light. It's 299,792,458 meters per second. And just like we round off 9.8 to 10, we round this off to 300. So 300 million meters per second, that's how fast light travels. And to give you a sense of how fast it is, it goes from the surface of the Earth to the moon in about a second and a half. So now we've got this number, 300 million meters per second. That's the speed of light. And nothing in the universe can go faster than this. So, oops. If the speed of light is 300 million meters per second, then what do you notice about the speed of light there and the two accelerations on the left? The speed of light is in between them. So the speed of light would go right about there, because this is 100 million, this is 400 million, and there's 300 million. So right about here is where the speed of light would go. Now, please note, this is a speed, and these are accelerations, right? But if I told you that Chad down here has an acceleration of 400 million meters per second squared, what's going to happen if he shines light up? So that's what we're going to do. Chad's got these three friends. He calls them over. They've got a laser pointer. So anyone below this blue arrow would not be able to escape. Even if they pointed a laser pointer straight up, like she's doing, that's Jane, the acceleration would pull the light back down and onto the surface of the Earth, where it would get stuck forever. Because the acceleration in less than a second is going to turn that light around. It's not going to be able to get out of there. Does that make sense? So any light could not escape our mini micro Earth way down here. You could never see the surface of this mini micro planet because light can't escape it. So what do you call an object in the sky that you can't see? It doesn't let out any light whatsoever. What do you call that? You don't see any light, so it's completely black. A black hole. So what we have, if we shrink down the mass of the Earth to a very, very, very small size, is a black hole. We can imagine shrinking down any planet or a star to a small enough size to make a black hole. And this is one of the things I love about teaching physics. We can just use our imagination to figure things out. And we can imagine stuff that normal people would have thought impossible. Because what normie would think of shrinking a planet to the size of a basketball just to see what would happen? And what would happen if you shrank the Earth to the size of a basketball? Nothing could escape it. The acceleration would be bigger than even the speed of light. So the force of gravity, which produces this acceleration, this tremendous acceleration, the gravity alone is going to suck everything down under the surface of the Earth. Please note, you would have to shrink the Earth to less than a kilometer. If it were at 2 kilometers, that would still be just big enough. So this guy could shine a light up and the light would get out, but this guy can't. What normie would think of shrinking a planet to the size of a basketball just to see what would happen? I like that. Blink. So next we're going to talk about how to make an actual black hole. First things first, you can't make one from a planet. Actually, you can't even make one from our sun. You need a star that is bigger than our sun. But before I get there, let me just talk about how our sun works. All stars work like this. So there's two main processes that go on continuously in stars like our sun. First, gravitation pulls the matter together and tries to crush the whole star towards the center. But fusion, exactly like those in a hydrogen bomb, heats up the interior of the star and all that heat pushes outward. When the processes of gravitation and thermonuclear fusion balance each other, the result is the sun of a given size. And there's the picture. Oops. There's the picture. Oh, let's read this. The heated material in the center of the star, all the fusion happens in the very center where the pressure is the greatest, moves outward. Heat is the kinetic energy of the atoms, and those atoms are moving fast, really fast. So, the white arrows represent the heat, which is made in the center, and that material gets heated up and it's pushing out, and it wants to move out, and actually moves up to the top, and then the cold material from the outside cycles back in. That's a little beyond what we're doing right now. The heat is pushing out. Gravity is the black arrows pulling everything in. So the sun has been going on for about 5 billion years, and it's in a nice, safe, stable place. There's no bouncing on the surface. Now, the size of the sun is the result of a tug of war between the two opposing processes. The immense heat from nuclear fusion pushing outwards, and gravitation pulling everything inward. Ta-da. If the fusion rate increases, if the white arrows were bigger, the sun would get hotter and bigger. Or if the fusion rate decreased, the sun would get cooler and smaller. If the white arrows got smaller, then things would contract. When the sun runs out of fusion fuel, hydrogen, gravitation will dominate and the sun will start to collapse. So someday the white arrows are going to go away because it's going to run out of fuel. And when the white arrows go away, the black arrows will win and the sun will collapse and collapse and collapse and get smaller, smaller, smaller. Now, like I said, the sun will not turn into a black hole. Have you ever taken an astronomy course or studied astronomy, maybe in middle school? Have you ever heard of red giant? So if you've heard of red giant, here's what happens. For our sun, once it runs out of hydrogen, it will expand into a red giant, and then it burns helium. The helium will undergo fusion and turn into carbon. During this fusion process, the sun will expand to become the type of star known as a red giant. So before it dies, the sun will expand out past the orbit of Venus, maybe even past the orbit of Earth. Yes, past the orbit of Earth, and it will be a red giant. But this will only last a few million years. And when all the helium is burned, then the red giant will collapse. So if you've heard of red giant, there it is. If you haven't, don't worry about it. So once the sun runs out of fuel, gravitation will dominate and the sun will start to collapse. It will no longer produce fusion, but it will still be hot and it will take a long time to cool down. And while it is still hot, it is called a white dwarf. White because you can see it, because it's still giving off heat. And it keeps getting cooler and cooler and cooler. When the white dwarf cools off down to room temperature, then it will no longer give off heat and light. It will then be the type of object called a black dwarf, because it's black. It's not giving off light and heat because it's cool, just like, the desk I'm sitting at. Now, our sun will not turn into a black hole. But if you have a star that is at least 3 times bigger, more massive than our sun, once fusion stops, or fusion is extinguished, gravitational collapse takes over and it doesn't stop. So when the white arrows go away, the black arrows push it in and keep pushing, 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 pushing. The star caves in on itself, and the atoms that compose the star cave in on themselves until there are no empty spaces. The whole star collapses to a point smaller than the tip of a pin. This is a black hole. Light cannot escape a black hole, as we said earlier, so you can't see it. But if there are other stars that orbit around it, you can see those stars orbiting something that is very heavy. So here is a picture that the astronomers made. There are these 3 stars. Those are very small stars as stars go. And there is the blue dot. The blue dot, they put that in the middle because that's where they think it might be located, somewhere inside the blue dot. I wish they didn't put the blue dot there, but I could not find a picture without a blue dot that they put in. So you don't see a blue dot there. It's all completely black. And we've been looking at this long enough that we can see these stars orbiting in those circles. We know they're orbiting there. So what's going to make a star orbit something? It's going to be something a whole lot heavier than that star. Just like the sun sits in the middle and the planets orbit it because the planets are so small, these stars are a whole lot smaller than what they're orbiting in that space. So that is proof of a black hole. There's something that's orbiting these, and we can't see it. Now, a black hole is no more massive than the star from which it collapsed. The gravitational field near the black hole may be enormous, but the field But the gravitational field beyond the original radius of the star is no different after collapse than before. The amount of mass has not changed. So there is no change in the field at any point beyond the distance of the original radius. Just like this, remember? The original radius of the Earth is at to here. And there's Randall standing on the candy apple crust. It's only when, what was his name, Chad goes down inside and gets close that the gravity gets really crazy and then things get dangerous. So if the Earth turned into a black hole, as long as you're this far away, you'd be perfectly fine. We could build a candy shell around a black hole and then just walk around on it. But once you get close, like inside the radius of what it used to be, that's when it gets dangerous. And that's what this just said. Okay? The gravitational field strength, how much gravity there is, near a giant star that collapses to become a black hole is the same before collapse, while the sun's still there, and after collapse, where there is no sun. There's a tiny little black hole in the middle there. So if there's a planet orbiting here and the star turns into a black hole, that planet is still orbiting there just fine. Just like Chad walking around on that. So to continue their story, astronauts could enter the solar system around a black hole out here, far away from the sun, and with a powerful spaceship still escape. After a certain distance, however, they could not escape when you're down and close, and they would disappear from the observable universe. Just like the guy, Chad, on the rope who went down from the candy apple crust and got too close to the black hole basketball Earth. So just don't get too close to a black hole and you'll be fine. And that is the lesson of the day. Don't get too close to a black hole and you'll be fine. In fact, I want to go all the way back to the beginning. Oops. All the way back. Oh man, I made a lot of slides. I got way too into this. What did we need to know? When a massive star collapses into a black hole, there is no change in the gravitational field at any point beyond the original radius of the star. This is what you need to know for the day. Yeah, I spent hours on this. I got a little crazy. Okay, so just don't get too close to the black hole and you'll be fine. Now, let me tell you a little bit about black holes. Near the centers of most galaxies, or near the centers of all galaxies, are immensely massive yet very small centers of force that cause the stars near them to speed around in tight orbits. Now, this was actually written years ago before we knew that they were a supermassive black hole. Supermassive black holes have only been confirmed in the last, 10, 15 years. These black holes are more than a million or more massive than a million suns. So we call them supermassive black holes. You can learn about them all over YouTube because SMBs are a popular topic on YouTube, here, there, and everywhere. Science people that tell stories about science love SMBs. And yes, every galaxy has one SMB at the center of the galaxy. That's a fact now, and we've observed it to be true in every single galaxy we look at. Every time we look at a new galaxy, and if we look in close, we see an SMB in the middle. And there's the end of today. So this was a long story. There are a few questions, and thank you very much. It was a lot of fun. Bye-bye.